Good morning. We are going to discuss our unit third, that is the solution of non-electrolytes. In this, we are going to see the various concentration units we are using in our life, in our laboratories. Then Raoult's law, then Gibbs-Duhem-Margulis equation. Then we will see the ideal solution for that vapor pressure in terms of mole fraction of gaseous phase, activity, chemical potential, and its thermodynamic consideration. The objective of this studying this is, after studying this, you will be able to describe the formation of different types of solutions. You will be able to express the concentration of solution in different units. You can state and explain Henry's and Raoult's law and whatever may be the special case. You can distinguish between ideal and non-ideal solutions successfully. You can explain how the real solutions deviate from the Raoult's law. Now, in our normal life, we rarely come across the pure substance. Most of the mixtures are containing two or more pure substances. Their importance depends on their composition. For example, brass, that is a mixture of copper and zinc. It's then mixture of copper, zinc, nickel, bronze, that is copper and tin. You get different alloys also. Now, in this unit, we will consider mostly liquid solutions and their formation. This will be followed by studying the properties of the solutions like vapor pressure, boiling point, and all. We will begin with the types of solutions and then various concentration units expressed. Now, solutions, these are homogeneous mixtures of two or more components. By homogeneous mixture, we mean that its composition and properties are uniform throughout the mixture. Generally, the component that is present in the largest quantity is known as solvent, which determines the physical state in which solution exists. One or more components which are present in the solution other than the solvent are solutes. So, we will consider the binary solution. Typically, there are such solute and solvent. In gaseous solution, these can be the solute, solvent must be gas. Examples are here. In liquid solution, solvent must be liquid and anything can be dissolved in that. These are the examples. And in solid solutions, solvent is surely solid and the solute can be in any phase. All the examples are here. Now, how the relative forces between molecules predict whether the solution will be ideal or non-ideal or heterogeneous? What will be forming? So, in ideal solution, when the two components act as if they are pure, an ideal solution obeys Raoult's law. Means volume of the solution will be equal to V1 plus V2. V1, V2 are the volume of the components. No heat is absorbed or evolved when the solution is formed. That is, delta H will be 0. When the forces between like molecules AA, BB, they are about same as that of AB, we will say that it is a ideal solution. But the like forces AA, BB may not be same as that of unlike forces AB. AB is the force between two molecules, solute-solvent, and AABB are the solute-solute, solvent-solvent forces. So when the unlike forces are stronger, molecules in the solution are more strongly attracted to each other than the pair. So the two components will mix to form the solution and the extra energy is given off. So delta H will be less than 0. Likewise, volume is expected to be the less than the ideal expected volume as the strong forces withdraw or bring the molecules closer to each other. But when the unlike forces are weaker than the like ones, the molecules are less strongly attracted. So energy must be added during the solution process. So delta H is greater than 0 and the volume will be larger than the expected. The like forces are larger than the unlike forces, a solution does not form and a heterogeneous mixture is produced. Like this. So these are the forces which decide which type of solution will be formed. Now, there are many different concentration units which exist because many different ways in which solutions are used in our life. Chemists usually are concerned with the moles of the substance. Other often may be interested in masses, volumes. So most concentration units express the quantity of the solute. What is the quantity of the solute in a certain quantity of the solvent to form the solution? So composition can be described by different concentration unit. So in real life, these we have to discuss. There are several ways in which we can describe the concentration of the solution quantitatively. First one is mass percent. We can call it as a weight by weight, mass percentage. Means what? It is the mass of the component in the solution divided by total mass of the solution, weight by weight. Many times it is written weight by weight, means what is the mass of that particular solute in the solution and the total mass of the solution. Percentage weight by weight means multiplied by 100. Suppose 10% glucose is in water by mass, means 10 gram of glucose is dissolved in 90 gram of water, resulting in 100 gram of solution. This unit is commonly used in industries, in chemical application. Suppose bleaching solution. Bleaching solution contains 3.6 mass percent of sodium hypochlorite in water, like this. Now next is volume percent. Volume percent defined as the volume of the component in solution upon total volume, volume by volume. Just like this, this is weight, this is volume, multiplied by again 100 as we are dealing with the percentage. For example, if I say 10% ethanol solution, that means 10 ml of ethanol dissolved in water. Total volume is 100 ml. So this is volume percent. Mass by volume means weight by volume. If we take this, weight by volume, generally used by in the medical field. Mass by volume means mass of solute dissolved in 100 ml, whatever may be the solution. ppm, parts per million. You might have heard ppm, parts per million. When solute is dissolved in trace quantity, very less amount of solute is present, and this is the unit which is used in pathology lab report or like that. You can usually see this ppm. Solute is present in very trace quantity. So concentration is expressed in parts per million. That is the number of parts of the component upon total number of parts of all the component multiplied by 10 to the power 6 million. As in case of percentage, concentration in ppm can also be expressed as mass to mass, volume to volume, mass to volume, whatever. Now, mole fraction. This is a commonly used unit in our lab also, by chemical engineers also. Mole fraction, commonly used symbol, X. Mole fraction is number of mole of the component, particular component, and the total number of moles. Means one component, number of mole of one component divided by total number of moles. We all are habitual of using this mole fraction, and total number of mole fraction of all the component will be surely 1. Then molarity. This also we use molarity. The number of moles of a solute dissolved in 1 liter or 1 cubic decimeter of solution. Molarity. In this, whatever may be the moles of the solute dissolved, but it should be considered in 1 liter. Suppose, and it can be indicated by a square bracket. Molarity. Moles of the solute in the 1 liter volume of the solution. Molarity. We can write down it as a m also. 0.25 m means 0.25 molar. Molarity. Molarity, moles per liter. It is a concentration, amount of substance per unit volume. This is very useful unit, especially for theoretical purpose. But because the volume of the substance changes with the temperature change, the molarity also changes. That means this molarity is a temperature dependent, because volume, we are saying the volume, and volume changes with temperature. That's why molarity also changes with temperature. So for precise work, a small change in temperature can alter the molarity. If whenever you are doing precise readings, you want more accurate readings, then molarity can be changed with a small change in temperature. Now molality, it is temperature independent. The problem with molarity was it was temperature dependent. So we come to molality, that is temperature independent. Molality defined as number of moles of the solid per kilogram of the solvent. Now this will not change with the temperature. So that's why it is independent of the temperature. Molarity is a function of temperature. So volume depends on temperature, but the mass does not depend on the temperature. That's why molality is independent of the temperature. And if you want to convert molarity and molality, we want to know the density of the solution. Then we can convert it. The two quantity, this molarity and this molality, that will be equal for very dilute solutions. For concentrated solution, values will be different. Now normality. Normality defined as number of moles equivalent per liter of solution. Like molarity, normality relates the amount of solute to total volume of the solution. However, it is specifically used for acids and bases. Now, how to calculate normality, molarity? We know some examples are given in your day-to-day life also, in your studies also. You are much familiar with these molarity, normality, all these terms. From the molecular weight, from the formula, you can find out all these terms. And whatever may be the concentration, whatever may be the percentage, whatever may be the volume, whatever may be the weight required to prepare such type of solutions. Now, we will see solubility. What is this solubility? Solubility of a substance means maximum amount of a solute that can be dissolved in a specific amount of solvent at a specific temperature. That is the solubility. Whatever may be the maximum amount of solute which can be dissolved, it should not be left undissolved. Whatever may be the maximum quantity of the solute that is dissolved in the solvent at definite temperature is the solubility. Naturally, it depends upon the nature of the solute, solvent, temperature, pressure. So we will see the solution of a solid or a gas in liquid. We will dissolve it. Now, solubility of a solid in liquid. First, we will see solubility of solid in a liquid. Every solid does not dissolve in a given liquid. NaCl, sodium chloride, sugar, they dissolve readily in water. Naphthalene, anthracene, they will not dissolve. Naphthalene, anthracene dissolve readily in organic solvent, benzene. Sodium chloride, sugar will not dissolve in benzene. So, polar solute dissolves in polar solvent, non-polar solute dissolve in non-polar solvent. We know the principle, like dissolves like. This we know. When a solid solute is added to the solvent, some solute dissolves and its concentration increases in solution. This is known as dissolution. Some solute particles, they collide with solid solute particles and get separated out of solution. This is known as crystallization. There are two processes, dissolution and crystallization. A stage is reached when these two processes occur on the same rate of forming the solution and of coming the particles out of the solution. That is the state of dynamic equilibrium, in which solute and solvent is in equilibrium with the solution. At this stage, concentration in the solution will remain constant, because whatever may be the solute particles are dissolving, the same will be coming out in the form of crystals. So this is the equilibrium under the given condition of temperature and pressure. Similar process, it is followed when gases are dissolved in the liquid solvent. Such a solution in which no more solute can be dissolved at the same temperature and pressure is known as saturated solution. The saturated solution is formed. Now, the solute will not dissolve in the solution. Unsaturated solution is the one in which more solute can be dissolved. So the solution which is in dynamic equilibrium with the undissolved and the dissolved solution, it contains maximum amount of solute dissolved. So concentration of the solute in the solution determines its solubility. Now, what is the effect of temperature on this? The solubility, it is significantly affected by temperature. Consider the equilibrium. In that, we must follow Le-Chatelier principle. If a nearly saturated solution, dissolution process is endothermic, means delta H is greater than 0. Means the solubility should increase with rise in temperature naturally. And if by chance it is exothermic, the solubility should decrease. This we can easily observe experimentally also. Effect of pressure. Now pressure does not have significant effect on solubility of solid in liquid. It is so because solid and liquid are highly incompressible and they are practically remain unaffected by change in pressure. Now solubility of a gas in liquid. Now we know that many gases dissolve in water. Oxygen dissolves only to a small extent in water. DO, dissolved oxygen, which sustains all aquatic life. On the other hand, hydrogen chloride, HCl, highly soluble in water. Solubility of gases in liquid, it is greatly affected by pressure and temperature. Solubility of gases increases with increase of pressure. For solution of gases in a solvent, consider a system shown in this diagram. The lower part is solution and the upper part is gaseous system at pressure P and temperature T. Assume that the system is in dynamic equilibrium. Under this condition, gaseous particle entering and leaving both will be same. Now increase the pressure. See, piston is lowered. Piston is lowered means pressure is increased. Means we are compressing the solution to a smaller volume, B. It will increase the number of gaseous molecules, particles in the solvent, in the solution. And the rate at which gaseous particles are striking the surface of the solution to enter it increases. So solubility of gas will increase till a new equilibrium will be reached with increase in the pressure. This was also the equilibrium at that pressure. But now as the pressure is changed, more gases will enter in the solution, it will dissolve in the solution and it will again reach to the new equilibrium at this increased pressure. So Henry, he was the first to give this relation between the pressure and solubility. His law states that at constant temperature, we have kept the temperature constant and increase the pressure. So at constant temperature, solubility of gas is directly proportional to the partial pressure of gas present above the surface of the liquid. Dalton also concluded that independently that the solubility of gas in solution is a function of partial pressure. If we use mole fraction, then we use this, where Kh is Henry's law constant. This is the Henry's law constant. At higher the value higher the value of Kh at a given pressure, lower is the solubility. It can be seen from various data which are available in the literature and I have given in the notes also. Now, Henry's law has various application in the industry also, in some biological phenomena also. To increase the solubility of CO2 in soft drink and soda water, the bottle is sealed under high pressure. So CO2 is dissolved in the liquid. In lungs, where oxygen is present in air with high partial pressure, hemoglobin combines with O2 to form oxyhemoglobin. In tissues, partial pressure of oxygen is low, so oxyhemoglobin releases to form oxyhemoglobin releases oxygen, which is used in the cellular activities. In deep sea diving, as nitrogen is more soluble in gas in our blood, and at deep sea, pressure increases, so its solubility also increases. When diver tries to come rapidly to the surface, pressure decreases and dissolved nitrogen in his blood starts forming bubble. So to avoid this situation, they use oxygen diluted with helium. Again, at high altitude, the partial pressure of oxygen is less than the ground level, so low concentration of oxygen in the blood and tissue of the people can be found. So these we can see the in a day-to-day life observations. Now the effect of temperature. Solubility in liquid decreases with rise in temperature. When dissolved, the gas molecules are present in the liquid phase and the process of dissolutions can be condensed similar to condensation and heat is evolved. Now the dissolution process involves dynamic equilibrium. Thus it must follow Le Chatelier principle. So as dissolution is an exothermic process, so solubility should decrease with increase in temperature because the process is exothermic dissolution process. The process of making the solution of gas in liquid, this process itself is an exothermic process. Heat is evolved. But if we still increase the temperature, definitely solubility will decrease. Now, vapor pressure of liquid-liquid solution. Now, liquid-liquid solutions are formed when solvent is liquid and solute can be gas, liquid or solid. But we are considering typically liquid-liquid. Binary solution of two liquids. Okay, so two components, that is 1 and 2. When taken in a closed vessel, both the components would evaporate and an equilibrium would be established between the vapor phase and liquid phase. Suppose total vapor pressure will be P total. P1, P2 are partial vapor pressure for two components 1 and 2. They are related to mole fraction X1 and X2. Now, we know that pressure P1 related to X1 by Raoult's law. Raoult's law states that for a solution of a volatile liquid, the partial pressure P1 proportional to X1, that is P1 will be equal to P10 X1 and P2 will be equal to P20 X2. So when we P total will be P1 plus P2. When we plot the graph of vapor pressure and the mole fraction of ideal solution, we are considering the situation when the solution is ideal. When A and B or component 1 and 2 are behaving ideally. In that case, this is 100% first, 100% second. This is P10. This is for second component and the total P will be in between these two. So the conclusion which can be drawn that total vapor pressure can be related to the mole fraction of any component. It varies linearly and depending on the vapor pressure of pure component, the total vapor pressure over the solution decreases or increases by the addition of the component. Now, there are some problems which are given on this, which you can see. Now, Raoult's law and Henry's law. In the last unit also we have discussed this, that according to Raoult's law, vapor pressure of a volatile component, it is given by this, P, Xi, P as 0. In the solution of gas in liquid, one of the component is so volatile that it exists as a gas, and we have already seen that the solubility by Henry's law is pKhx. If we compare the Raoult's law and Henry's law, it can be seen that partial pressure is directly proportional to the mole fraction. Only the proportionality constant is different. Here it is Pi0 and here it is Kh. That means Raoult's law is nothing but a special case of Henry's law. In both the situation, the partial pressure are proportional to the mole fraction. The different quantity is Pi0 and here KH. Only its value changes. Now, vapor pressure of a pure solvent. The decrease in vapor pressure of pure solvent, this is pure solvent, 1, and we are decreasing its amount. It depends on the quantity of a non-volatile solute which are present in the solution irrespective of its nature. Suppose we can observe that decrease in the vapor pressure of water by adding 1 mole of sucrose to 1 kg of water. It will be like this. So if we add 1 mole of sucrose to 1 kg of water and 1 mole of urea to 1 kg of water, the decrease will be same. What I mean to say that the decrease in vapor pressure of solvent depends on the quantity of solute added, not on the nature. In both the situation, in sucrose and in urea, we are adding 1 mole. That's why the situation or the decrease will be same. Now Raoult's law can be stated as for any solution, partial vapor pressure of each volatile component is directly proportional to its mole fraction. So when a component is nearly pure, this is proportional to, this is Raoult's law. When real solution at low concentration, the constant of proportionality is not the vapor pressure, but it becomes Kb. That is Henry's constant that we have seen that. If it is ideal solution, we are going with this. And if it is very, very dilute solution, then we will go with this. So such solutions are called as ideal dilute solutions. Ideal dilute solutions. Now we will see the expression of total vapor pressure in terms of mole fraction in vapor phase. Now for binary solution, Raoult's law, it gives the relationship between the total vapor pressure and the liquid phase composition, P, related to mole fraction for first component, for second component. Suppose we are considering this x1 and x2 are the mole fraction in liquid phase and y1 and y2 are the mole fraction of the two components in vapor phase. We have to find out the expression for total vapor pressure in terms of mole fraction in vapor phase, that means y1 and y2. We are going to find out the relation between P, total vapor pressure P, and the mole fraction in vapor phase means y1, y2. We want to find out the relation between P and y1, y2. We know this for liquids. We know this for vapor phase. When we combine these two equations, we combine P1 and P2 from these two equations, we can get this. Now what is total vapor pressure? It is the combination of P1 plus P2. We are just going to add simply this. Following some mathematical steps, we can find out the value of x2. Putting this value of x2 here, we will get this. Or we can reach to the conclusion that P is equal to, this is the simple mathematical derivation which can be asked in the exam many times. This equation shows variation of P with Y2, means mole fraction of the second component in gas phase, Y2. But if we want to see the variation in terms of both, then it is 1 by P is equal to this and this. Just I have taken 1 by P. Reciprocal of this you can also take and then separate the terms, you will reach to this equation. Now this is the graph between pressure and mole fraction. See, this is for pair B, this is for pair A. In between, this is liquid, this is solid, and liquid and gas both. This is liquid, this is vapor. In between, both liquid and gas exist. Now about the activity coefficient. Now activity coefficient. At intermediate concentration, in many cases, neither Raoult's law nor Henry's law holds good. because we have given the condition when Raoult's law holds good, when Henry's law holds good. But suppose many times intermediate concentration, both the law doesn't hold good. In these cases, if the solvent standard state is assumed, then the activity is determined by the vapor pressure. It is a product of mole fraction and the quantity, this activity coefficient, mole fraction and activity coefficient, mole fraction. If the solid standard state is assumed, then the activity expression is related to this. Again, it is Henry's law. In some applications, solid standard state activity is related to molarity. So, activity can be expressed in different ways. What I mean to say that if whatever we have the term, we can relate it with the activity. So, we have thus considered the variety of chemical species in different topics. We have considered the gases, we have considered pure liquid and solids, solutions in standard state, solution and solute in the standard state. We have related the activities, we have seen the concentration units also. So you should be able to solve the concentration problems, and you can successfully use the term activity and activity coefficient for the system of different consideration. Thank you.